NASA released this video about the magnetosphere, and I wanted to go over it with everybody because this is 2019 and everyone's still using 1957 Van Allen belt studies. And while it is an accurate description to describe what we understood when we were first going into the mesosphere and the lower thermosphere, well, it's not the last days of the Apollo mission, and where they're not rendezvousing with the Soyuz anymore, and so we can move past that. So now in 2019, we understand a great deal more about the Van Allen belts and all of the properties of the magnetosphere, and calling them the Van Allen belts is just kind of outdated, and really it leads to nonsensical arguments. So I'm going to put all of the arguments to end now with this simple video. I want to describe and show to everyone, give a good idea so that they can all understand exactly what the magnetosphere does, why it's so important, and how it is that the properties that we're experiencing and we're used to on Earth, what we talk about, and the radiation and all the particles that we measure on Earth are different than the particles we measure in outer space, about 230 miles up, as opposed to the particles that we measure out 25,000 miles out in space when we start to get into deep space and we leave the Earth's magnetic properties. So this video is going to explain how, I like to give the example that if you have a rock and you take that rock and you put it in the middle of a river, and now that river is, soaking it, and if you just then made an invisible shield for that rock that shielded all of the water while it's still in the middle of the river down there underwater, shielded it from ever getting wet by the water that's just pouring around it as it goes downstream. So that rock right there, it does receive some of the water from it, but let's say that the water it receives from it is just the condensation that's built up on the inside of that bubble. And that condensation, it never even drips. It's just maybe a couple of dew drops. However, where it doesn't drip, occasionally one of them explodes and atomizes into thousands and millions of little tiny dewdrop in little particles that float around and just do various random things inside the bubble. Some of those, maybe 1% of that 1% that accumulates on the inside, it touches that little rock. So, if this rock was the Earth and the river was solar energetic particles, the consistent of light and mass that's not only coming from our sun, but other celestial bodies that have soaked up the rays from the sun. If you notice, the moon puts off as many gamma rays as the elephant foot from Chernobyl. You'll notice that we're contending with celestial bodies like Jupiter that's heavy behind us, and the celestial bodies around us, as well as the star that gives us everything that we have. And then, of course, cosmic background radiation that comes in out of nowhere, gamma rays and cosmic background radiation that just saturates our solar energetic particles and cuts through them as well, because, well, learn how linear accelerators work. All of these things are a very strange yet very necessary anomaly for all of life, or the lack of life, to be. So this magnetosphere video that they presented, it has a lot of irregularities with the graphics, and I'm going to touch on a couple of them, but mostly I want to point out that this shows constantly, in every way, that we only receive down at the International Space Station, gets 230 miles up, gets 1% of what is above it in the plasmasphere, above the exosphere, on top of the thermosphere and exosphere, and the plasmasphere right there. From the plasmasphere to the magnetosheath, on all of that, what the ISS gets is only 1% of what's in right here. And so outside of the plasmasphere and the magnetosheath, outside of that, and outside of the bow shock and the magnetosphere's, the end of it, well, that's 100% of all of it. That's being in the river. So here's a bunch of graphics explaining what everyone seems to not understand, and that is you cannot go with a craft into the sea without having the magnetic fields that the Earth has on your craft. So if you want to leave Earth's magnetosphere, you have to have it. Apollo never went to the moon. It went 230 miles up. All of these graphics show and back up GSI and Princeton and UCLA and Berkeley and all of the rest of the prestigious universities that have stated very clearly the science as to why these particles are heavy. Bicarbon-14 will immediately end up causing damage to the nucleus and destroy all of the DNA, and your RNA released will end up causing irregularities, and you'll have cancer and die. So this is everything visually you need to see.
Earth's magnetosphere. Presented by
Goddard Heliophysics Channel, NASA.gov. It's good stuff. First concept of the Van Allen belts, now outdated. Then they started adding them more. This is an outdated and inaccurate graphic, simply because, well, this is not the magnetosheath, so this is not the bow shock, clearly, as this film would be, I'm guessing, the atmosphere. We're still in the atmosphere, so within this film, that would be the International Space Station. So I guess what they're trying to say is this is just the magnetosheath. However, now they're discounting and disregarding all of the inner bands and everything that those electromagnetic points would have to do. So this graph, it's nonsensical. It's missing everything, and it doesn't describe anything. It's trying to talk about the north and south poles and how the polar cusps assist in that, but not very well at all. However, this was obviously leading into them being able to talk about, if we were not with that, we would be like Mars. We need to have this, because if, Mars ever had a magnetosphere and was like Earth, well, obviously, it would be stripped away. Another inaccurate graphic here. Note, particles don't go around things that don't have electromagnetic shielding. None of this would be curving right here. All of it would just be absorbing. I mean, some of this might be carbon if carbon is crashing into it, and it may displace particles, but that's highly unlikely. The ionization that would have occurred would have already stripped everything that is capable of being taken off. The Mars planet now, bottom line, it's just a giant ball of radiation. It has to be. There's no magnetospheres keeping the 700 millisieverts a year that we claim, 700,000 millisieverts a year that we claim the radiant environment is, which means, as that's all carbon and iron and hydrogen and helium, heavy ions, that right there is as radiant as Chernobyl elephant foot. To stand on it's impossible, let alone to take the radiation that's still hitting it and would have been hitting it long before we got there.
Possibly after the red planet's magnetic field dissipated.
It never had one. Just never had one.
Where in the world we see today, through the
See?
eyes of NASA orbiters and rovers.
This is the Chilean mountains. It's the Atacama Desert. And you want to know how climate change works with the magnetosphere? It's really easy. There's a global circuit, and just as things are ionized and everything falls down after being pulled up out of the earth, not everything falls back down. For the same reason that we have lightning, we also have sprites. We are losing certain properties as fast up as they are down. That's why we're not getting raised seas. None of the oceans are going to rise because we're losing hydrogen and oxygen at phenomenal rates and water levels. We're losing O3 as we did much, much earlier. I was a kid when I was being told that aerosol was killing the ozone. And now we're being left with heavy carbon potentials and all of our wonderful byproducts from our cars, and potentially a bunch of nitrates like ammonias and stuff. So obviously we're going to turn into Venus, and we will get hot, and we will burn, and there will be heavy winds, and we will be heavier ionized, and that's our future. And it's all because the magnetospheric bands and human interactions with them are causing this to accelerate, and the seas aren't going to rise. We're eventually going to boil, though, and we will become sulfuric and hot.
Our atmosphere protected. After he is Zesta of the geospace.
I like this map the most because it gives the best description of the size, because now they still give you the film, but they gave you the length of the bands, showing that the North and South Pole would have had a great deal of stretch to the polar cusps. There would be, like here, they kind of give an example as to where the first, the plasmasphere would be, and that gives you an idea as to the inner, I guess, Van Allen belts, if you want to talk about those being. However, some people want to refer to the inner plasmasphere and the outer magnetosheath as the Van Allen belts. Still doesn't work very well, because out here would be the magnetosheath in between these points. So you can't really say that these bands right here are the magnetosheath. I've got a great graphic that I like to refer to. I actually got it from a Indian professor, and they did a wonderful write-up. It's kind of hard to find. I will put a link in the comments for it, but this graphic right here, it has the best way to show, to scale what everything is. I made a little video about it and talked about the levels of everything using that map to scale. If you haven't seen it, you should check it out. But the thing I want to point out here is, once again, constantly in every single one of their artist renderings and all of the graphics that NASA has to make, every single time, see the constant? Now these are not solar energetic particles that are from any type of solar storm. This is not from a coronal mass ejection. These are not from solar flares. This is just the basic solar energetic particle, light and mass, that is consistently radiating from the sun. Like we all saw, you know, the solar eclipse. I got a couple of great pictures and videos of it. And when I saw it with my naked eye, it just confirmed for me once again, as it's like the third solar eclipse I've been privy to seeing, that the solar energetic particle consistent is an amazing and vast thing. It proves and shows, not only to the naked eye, but in all scientific measurements, that we are in an ocean, a sea of plasma. And for some reason, we have this invisible shielding keeping this water, this plasma, off of us. And occasionally, some of it pops through, which is what they're about to talk about now. So as all of this, the 100% goes away, sometimes 1% makes that through. And when that 1% makes that through, it starts to interact with those inner bands. And as those pull them around, we start to find a turbulent state. And so as it pushes through, they reconfigure their placements, and the bands occasionally pop. So sometimes when there's so much, now this would be the magnetosheath I keep referring to. And the magnetosheath, whenever its plasmic state gets so heavy, it forces 1% within a band to ride down, and it comes down in kind of a heavy charge. And that, of course, works with other ones, and that 1% eventually makes itself to 1%. Now, way down in there, that's our atmosphere. And deep down in here, 230 miles up, and this is 25,000 miles out, but at 230 miles up right here, where the International Space Station is, we get 1% of this 1% that makes it from this 100% right here. So, we are fine on the International Space Station. As GSI's Marco Durante says, passive shielding is a solution on the planet, but not within transit. You need active shielding, like this, to be out here in transit. Or, like on Mars, as we just showed, it's ionized, it's being hit, doesn't have any of this shielding. You would need shielding on Mars to be protected from Mars because it's radiant, as well as the things coming down onto Mars, making it radiant. So, this is electromagnetic reconnection points that I'm always talking about in my videos. And this is how it is that we get 1% of the 1% that is the mass of the constant light and mass from our star, as well as other anomalies. So it is always just a brief moment. Now see, this is that clump that I was saying. It's just one particle mass from the mass of particles that makes it through. And it usually, when it hits, it shoots itself into various positions, and not all of that makes it through. That's why it was a stream, is sometimes it's a burst, sometimes it's a small amount. That's how we get the aurora borealis, though, is that they start to follow through north and south polarity points, and eventually, when they come together, the fields, the north and south points, they cross. And just as we're always talking about a polarity flip happening on Earth, it's because all of these north and south lobe type poles are constantly flipping, not only within the electromagnetic fields of the magnetosphere, but also in smaller regions here on Earth. Like if you look at your local weather, you'll find that the north, and like all of the high and low pressure fronts that they talk about, and sometimes when they swap or how the bands twist around each other, if you follow heliophysics, you'll see that on the sun, you'll find sunspots and Alpha waves act and respond in the exact same way as our storms do, and it's all because of the phi flip and the electromagnetic fields that change polarity so frequently. And this is what happens, even occasionally when that happens, we get the aurora borealis, which causes anomalies in weather. It was very easy to track the coronal holes and the new sunspots that came during the time in which Dorian was coming towards and going over the islands. It's almost exactly hour to hour, the position and the amount of X-ray, gamma ray And alpha beta particles that were affecting our magnetosphere show how the effects of the stratosphere, play into that and how it affected the path and the intensity of the storm. And eventually we're going to start touching on how climate change and the magnetosphere are hand in hand. But here's how that happens. Now most of it is dispersed and lost. However, many of it travel back with one of those bands. It either heads back out or it heads down in. Now this is my favorite and one of the most recent models that we've given. Now this gives one of the best to scale graphics of everything that NASA's been able to do. Now I want to point out with this graphic right here, one of the things that they do a good job on is showing not only the fields of magnetic reconnection points that are occurring here, and something that the MMS mission just found in 2018, and then again in 2019, this year, they found it happening up front here within the frontal band entry bands in the magnetosheath. And so not accounted for within these bands right here, because this is not all of the magnetosphere. However, within these fields right here, they have found that there are more in front than behind that make it into our system. That's why the previous model showed more electromagnetic reconnection points coming from our frontal north lobe than through the electromagnetic neutral points that happen in the tail. So.
Magnetic reconnection triggers such a violent explosion, opening the rifts into the magnetosphere. NASA's Magnetospheric Multiscale Mission, or MMS.
Very cool. Themis, all of these missions, most important thing humans have ever done. Absolutely.
Wrestling with energetic particle detectors and magnetic sensors, the four MMS spacecraft flew in close formation to areas on the front side of the Earth's
They eventually started to spread out, and this year that's how they found the new electromagnetic reconnection points within the magnetosheath.
MMS complements missions from NASA and partner agencies such as Themis.
So I want to point out right here that these are not to scale. So Themis is not to scale, and Geotail is definitely not to scale. So this entire graphic is not showing the accuracy. They're showing this is where the sun's points are, and this is the Earth's elliptical orbital pattern. However, within the magnetosheath's fields here, they're not actually describing the pattern of movement correctly, or at least to scale. This may be correct if this was just encompassing the plasma sphere, but then they're not accounting for the rest of the Earth's magnetospheric bands.
Cluster and Geotail, contributing critical new details to the ongoing study of Earth's.
However, they are redoing these missions to assist in the new Artemis mission, and more proof that they repurpose everything, because it's expensive to make these, and there's only so many of these tools out there. So the most recent mission is going to be the Parker probe. They're hoping that the Parker probe is going to be capable of touching the plasma sphere. If we can touch one of these raw particles, then most likely we'll be able to study them more than GSI has presented. That is proof, consistent proof from NASA. Not only do we need the electromagnetic shielding on our crafts to leave them, as NASA and Berkeley and GSI and Princeton and UCLA and all of them have stated over and over and over again. But the reason why that is because in all their graphics and all ways that they show, whether it's accurate to scale or whether they included all the bands or not, they're always showing that the consistency of the mass and light out there is greater than anything we've experienced while safely within Earth's magnetic shields, and we don't understand what makes them, and we can't make them yet. And until we can make them, we're confined to them. So go Parker probe. Here's hoping we heliophysics and Goddard and everybody continue their understanding of it. And we work together with JAXA and ESA and Roscosmos, and India's putting up new systems, and everybody's working really hard on solving these problems so that maybe soon we can send robots 1,000 miles up to where we lost 2 out of 3 of the Apollo 13 members for going, because, well, 230 miles is where we are for a reason.